Welcome to the OCR-A G482 Module 5 video on the photoelectric effect. First of all, we'll start with a basic explanation of what the photoelectric effect is, and move on to talk about how it provides evidence for the particle nature of light. Well, the basic setup you have is a metal, and at that metal you fire a photon, which is absorbed, and it causes an electron to be emitted from the surface. That, in essence, is the photoelectric effect. Now you need to know a lot more detail than that, so we're going to look first at a qualitative picture of how it works, and then move on to talk about an experiment you can do where you can get some actual quantitative measurements of particular quantities. Okay, so the simple, if you like, experiment to demonstrate the photoelectric effect is with a gold leaf electroscope. Now the gold leaf electroscope works because light charges repel. So if the electroscope becomes charged, then the gold leaf will be repelled, and because it's very light and has extremely low weight, that repulsion will be sufficient to cause it to raise upwards. Okay, it's the same sort of effect that you get when hair stands on end if you are being charged up by a Van de Graaff generator. Okay, so how does the experiment work? Well, there's a sequence of things that you have to do. First of all, you have to earth the plate on top of the electroscope, the metal plate that you're trying to demonstrate the photoelectric effect with. The reason you do that is so that you can charge it up in advance. Okay, an earth connection is essentially an unlimited source of electrons, and it's also an unlimited what we call sink for electrons. So electrons can flow to and from Earth, and it doesn't really affect the potential of Earth, so we can get as many as we like. So what we do is we connect the plate to Earth, and as it stands nothing happens, but then what we do is we bring a positively charged rod towards the electroscope. That attracts the electrons from the Earth onto the electroscope. And because the electroscope is now charged, the gold leaf will raise up. Okay. Then what we do is we remove the Earth, and then we remove the rod. And that essentially traps the electrons on the electroscope. It's now negatively charged, and the gold leaf remains up, provided the electroscope doesn't leak. And then what we do is we introduce our incoming photon. It does the same thing. It knocks off one of the extra electrons this time. Obviously that means there's now less charge on the electroscope. The remaining charges kind of redistribute themselves, and the gold leaf drops a little bit. So if you kept doing this process, if you kept firing photons, if a continuous beam of photons coming at the plate, the gold leaf would gradually drop down as the electroscope was discharged and all those extra electrons were removed. Okay, so that experiment doesn't tell us very much about how the photoelectric effect works. It just tells us that it is happening. We know there are electrons on the plate to start with because we've put them there with the induction charging that we did. And we know if the electroscope, the gold leaf goes back down, those electrons must be being removed by the photons. So this proves that the photoelectric effect is happening. Okay. Now, what's actually going on then is essentially a conservation of energy. The incident photon has some energy given by HF, and its energy is then divided between two different types of energy to eject the electron from the metal. The first part is essentially the binding energy of the electron in the metal. It's called the work function. Now the work function is a very particular binding energy. It's the least amount of binding energy we can have. So it's the minimum energy required to remove the most energetic electron from the surface of the metal. You need the minimum and most in that description, because if you put more energy in, you can still remove the electron, so that would be more than the work function energy. And we have to talk about the most energetic electrons because we want to talk about the minimum amount of energy we have to put in. So we'll see in a diagram in a little bit why the minimum and the most are necessary there. The remaining energy from that photon goes into kinetic energy of the electron. And so if we've put the least amount of energy into getting the electron out of the metal in the first place, that will mean we have the most amount of energy left over from the photon to remain as kinetic energy of the electron. So that's why we have this. The work function is a minimum amount, and the kinetic energy in that expression is the maximum amount. it is entirely possible to divide the photon energy up in a different way to that. This is just the most useful expression of conservation of energy because it deals with the extreme case. To try and get an idea of how that works, we can look at a simple analogy with the band structure, the electron energy level structure of an atom. So for a single atom, you've got electrons in the energy levels, 2 in each, and especially those of you who do chemistry, first ionization energy is essentially the minimum energy required to remove the outer electron from a given atom. Okay, in this case, I've just made up an energy level structure. It's 2.4 electron volts. So if I was to take a photon and fire it at this atom, it would need to be at least 2.4 electron volts to eject that outer electron and ionize the atom. Work function is essentially the sort of bulk analog of first ionization energy. When you put all those atoms together to make a big lump of metal, instead of electron energy levels, you end up with this band structure here. Now, you don't need to know anything about how that works at all, but it's useful to see the analogy. And the sort of big blob of red in this bottom band and the smaller blob of red in the second band up here represent all the electrons in the entire metal. So there's billions and billions and billions of electrons in these two levels. But essentially the work function is the same thing as the ionization energy. If we were to fire a photon at this metal and it were to hit the most energetic electron right at the top of this second band up, that's the amount of energy we would need to get it out of the metal surface. Okay? So that's a simple model for it, kind of trying to explain what the work function is. Obviously, as I said before, if your photon energy is a bit more than it needs to be to get the electron out, it can hit an electron further down, one that's more tightly bound. Okay, so it can hit one where you'd need more than the work function energy to get it out of the metal. If that happens, then obviously that electron will have done more work to get out of the metal, and therefore will have less kinetic energy left over. So it won't be the work function of maximum kinetic energy now. It'll be something a little bit more than the work function and less than maximum kinetic energy that we've split that photon energy into. Okay, so how can we get at these numbers, the work function and the kinetic energy, and look at them in an experiment? Okay, so the experiment we have to do here, which also lets us determine Planck's constant, uses this apparatus here. This is basically a potential divider circuit, which you should be familiar with from the earlier modules, with it attached to this photocell here. Now, I've got an electron shown on the plate already. You have to imagine that electron is actually in the plate here. It's in the left-hand plate of this photocell, which is the positively charged one, okay, the anode. Now, what happens here then is that if we have the potential divider in the position we've got shown here, there is no potential difference across the photocell. So the photon comes in, knocks the electron across. If it gets across the photocell, it ends up going round the loop through the microammeter, which measures a current. Okay, and that's with 0 volts across the photocell, because the potential divider is on the left-hand side here. Okay. Now, if we move the potential divider until we get to a particular voltage called the stopping potential, then instead of the electron getting across the gap, the left-hand plate is now at a positive potential and the right-hand plate is now negative. So the electron, if it's ejected, will get attracted back towards the plate it's been emitted from, the left-hand one. And if you get the potential difference exactly right, then even the most energetic electron will not get across to the right-hand plate. So something like this happens. The photon comes in, boomf, and the electron doesn't quite manage to get across before it's turned round and hits the original plate. Now there, it does not, whilst it's still ejected from the surface, it does not go through the ammeter, so there is no current registered. Okay, and if we go in between these situations with the potential divider position, I think you can see that if we put the potential divider halfway between 0 and the stopping potential, there's going to be some electrons getting across, the ones that happen to have maximum kinetic energy, or upper half kinetic energy, but the ones with not quite as much kinetic energy will fall back again. If you want to see this in a simulation, there's a link on the top right hand side here which you can put in, which is a FET simulation for this. Instead of a potential divider, they just use an adjustable voltage supply, but it does exactly the same job. You can also fiddle about with the incoming photon energy and intensity, so you can play around with the parameters and see what happens. Okay, so that's the basic experimental setup which you need to be able to talk about. Now, well, how can we interpret the results? Well, if we've taken sort of the two extreme readings here. If we take a bunch of readings in between these points, we can plot it on a graph. Just down here in the bottom right hand corner is just the fact that if we think about conservation of energy, this experiment provides us with a nice way to measure the electron maximum kinetic energy. That's tricky to do directly. You can't, time the electron very easily. So what we say is that the work done just at the stopping potential, so that the most energetic electrons don't quite make it to the right hand plate, is going to be equal to the stopping potential times the charge on the electron. That's W equals QV. Okay, so that's how we get the stopping potential and know that it's equal to the maximum kinetic energy. That's going to be important for the next slide. Okay, so here's the results of our experiment. Let me walk you through this because it kind of looks a little bit complicated to start with. We've adjusted the potential difference. That should really say potential difference. The stopping potential is a very particular potential difference. And what we're doing is we're looking at how the stopping potential varies with photon frequency. Okay, so we're changing the incoming photon frequency and seeing what happens to the stopping potential we need to get zero current. Okay, now because it's a particular metal, there will be a minimum photon frequency we need to get the electrons out at all. That's essentially the work function energy. When the photon frequency equals the work function energy, we're down at this point here. Okay, we can't take any measurements below that photon frequency because there are no ejected electrons. Okay, the photocurrent doesn't exist. So this dotted line is extrapolation here. And as we might expect, if we increase the photon frequency, right, for a particular metal, okay, then there's more kinetic energy left over to go into the electron's kinetic energy, right, and therefore we need a higher stopping potential, and they're proportional, right. And we expect that because we take our original expression of the conservation of energy and replace the electron maximum kinetic energy with our expression for the work done in going across the photocell on the electron, this EV here, which is equal to the maximum kinetic energy. Then we get this second expression. If we rearrange that and do our quantitative practical matching with what we've plotted, for exercise, you can check that you're happy that the second equation here rearranges into this third one. Then we get V equals H over E times F minus phi over E. If we match things up, we've plotted V on the y-axis, we've plotted F on the x-axis. That means the gradient of this graph is Planck's constant over the charge on the electron. And this extrapolated y-intercept here, because remember we can't do the actual readings in this dotted region, gives us the negative of the work function over the electron charge. Okay, so from this single experiment we can determine the work function for the metal and Planck's constant. Now this tells us a lot because it tells us how the results would look different for different metals. Using a different metal obviously doesn't change Planck's constant, so all the lines should be parallel if you have different metals. However, different metals do have different work functions, so the whole set of data will basically move up and down depending on the metal. Okay? So, the one other thing to notice is the x-intercept has a particular meaning here, which we kind of discussed before, which is when you don't need any stopping potential, right? If you look at the equation up here, if we just put EV equals 0, then we get HF equals phi. And that gives us the particular F where you won't get photoemission below this F, this frequency. That we call the threshold frequency, and this expression here, HF threshold equals phi, is how you would calculate it. Okay. So just take a moment to make sure you're happy with all the features of that graph and how they relate to the equations, and replay the explanation if you need to a few times, because it can be quite tricky. The last thing we need to know about is how the various input parameters of the experiment, so that's really photon frequency, intensity and stopping potential, have an effect on the photocurrent. We've kind of discussed it, but you need to have a very clear understanding of what happens in each situation, because you could be asked. So situation number 1, how does the light intensity, when we keep the photon frequency fixed and assume we've got no potential difference across the plate, so we're just observing the photoelectric effect here and not trying to use the stopping potential. So how does light intensity affect photocurrent? Well, there's two different regimes here. Below the threshold frequency, the photocurrent is 0. There are no emitted electrons, and this is actually what gives us the evidence for the particle nature of light. If it were possible to gradually build up energy in a kind of wave-like fashion from multiple different photons giving their energy to an electron, then we would get electrons emitted below the threshold frequency. Because we don't see that, that gives us a clear picture that it must be one photon giving its energy to one electron in a collision, and it's not a sort of gradual wave-like build-up of energy. Above the threshold frequency, as you might expect, the photocurrent should be proportional to the intensity, because the number of photons, for most light sources, the number of photons in the beam is proportional to the intensity of the beam. Okay, if you double the number of photons, you will double the intensity. Okay, so that means twice as many electrons ejected, and therefore twice as much current. Okay, next situation. How does the photon frequency at a fixed number of photons per second affect the photocurrent? Now, this is tricky. I've said a fixed number of photons per second rather than a fixed intensity, because there's a slight problem here. If you think about it, intensity is energy per second per unit area. We can forget about the area for the moment and assume we're just talking about the same area being illuminated on the plate. So really we're just talking about what happens with energy per second. If you keep the energy per second constant but change the photon frequency, what you are doing is having the same total amount of energy arrive in 1 second, but at higher photon frequency, that is fewer photons, each carrying more energy. Okay? So that's quite complicated. It's much simpler to say same number of photons per second arriving. How does the photon frequency have an effect? Again, this is something that probably you won't get asked. The most likely situation is they will ask you about the slide you just saw. This would be a very much upper end question. Okay, so if you're struggling a little bit, don't feel like you need to continue past this point and try and understand this. You've probably got enough to be okay. So, if you increase the photon frequency, it does increase the photocurrent, but possibly not for the reason you might expect. Thinking about our conservation of energy, increasing the photon frequency for a fixed metal will increase electron maximum kinetic energy, but that's not why the photocurrent increases. Okay? And it explains in the text here, right? The reason the photocurrent increases is because we've got a larger probability that we'll actually get a photon colliding with an electron it can get out the metal. If you think about the situation at the threshold frequency, we have to be incredibly lucky, and that threshold energy photon has to hit one of the least well-bound electrons in the metal so that it's got enough energy to get out. Okay, that is incredibly unlikely. As you increase the photon energy, you gain access to a larger sort of proportion of the electrons that you can actually get out the metal. Okay, now they won't all come out with maximum kinetic energy, but remember, they don't have to. They just have to come out with some energy so they can get across the gap and go through the ammeter. And what matters there is not how fast they go across the gap, but how many go across the gap in a second. Because that's what current is. It's charge divided by time. The total number of them that get across the gap per second. So because A higher photon frequency means more of the photons will cause an electron to be emitted. A higher photon frequency will also mean a higher photocurrent. Now, the precise nature of that is a bit complicated. It's not necessarily proportional, but I think that's enough for us to talk about the trend. Okay. The other graph that you might need to explain is the effect of the potential difference across the plates in the photocell on the photocurrent. And again, there are some slight complications with this, but our simplified picture looks like this, right? When we have the experiment set up as we did previously, where the potential difference is trying to stop the electrons getting across the gap, it's accelerating them back towards the emission plate, then as you might expect, and as we've already said, as we increase the magnitude of that potential difference, we decrease the photocurrent. By convention, we say that that is a negative potential difference across the plates. Okay, so when we're trying to stop the electrons getting across, we count that as a negative potential difference. So we get to some potential difference and the photocurrent drops to 0, and when we get to that potential difference, that is the stopping potential. Okay, and as we decrease the potential difference, as you might expect, more electrons will get across the gap until we get to the point where, technically, at the point where there is 0 potential difference across the plates, all of the electrons will get across the gap. There are issues with the fact that some of them will not be heading directly for the other plate. Okay, so partly for that reason, sometimes you'll see a lot of variation in these graphs. Okay, sometimes there will be a slight increase beyond this 0 potential difference line, because having a slightly positive potential will mean that some of the electrons that were sort of flying off in the wrong direction will eventually end up hitting the plate. Okay, so you will often see this increasing past this 0 line, but it will still reach a maximum point where you've got that potential difference big enough that any electrons that are ejected from the left-hand plate will end up on the right-hand one. And that depends on the geometry of the photocell and other things like that. So it's not a simple thing to explain why sometimes it would go up past the line, but it does sometimes if you see them in an experiment. And that's literally because you just get those ones that weren't going to hit the right-hand plate. Okay, so and then if we kind of swap the direction of potential difference around, and this time we're trying to accelerate them across, then as I basically said, it doesn't matter how fast they get across the gap, it's just the number that are emitted. Putting a larger potential difference across the plate below the point where you make a spark happen, which would be thousands of volts, won't make any difference to the number of electrons that you get across. All it'll do is means they get across the gap faster. But the number that go through that right-hand plate per second will not be affected, and therefore the current will not be affected. Okay? So that's the basic shape of that graph. And the one other thing that you might have to do is to look at that graph and how it changes with intensity. This is kind of combining the arguments for that graph and what we've just talked about with the effect of intensity. As we said, increasing the intensity for a given photon frequency would increase the photocurrent. It should be proportional. You've got to be careful. It won't change the stopping potential, so all the graphs will start at the same point on the left-hand side, but they will just peak at a higher photocurrent when you get to 0 potential difference across the plates. And as I said before, different photon frequencies, same intensity is complicated. There are lots of competing factors which are described in the text here. If you get asked that, that's just a horrendous question, and they can't reasonably expect you to answer. You don't really have all the information you need to answer that properly. So if it does happen, you could talk about these two things and the fact that it's difficult to balance the two factors. The fewer photons per second, but each one has a larger probability of causing an emission, means that those are two competing factors. It's difficult to say whether they're going to go up and down without doing a calculation. Okay? Right. That should be everything, and probably a little bit more than you need to know about the photoelectric effect. Do re-watch sections if you're not happy with how it works, and email me any questions before the exam if you need to. Thank you very much.